So without further ado, I would like to welcome you all to Entropy, an event that aims at acquainting you with entropy in different subjects and dispelling the misconceptions associated with it. Our first speaker for the day is Professor Arnab Mukharjee, speaking for chemistry.
Okay, so I'd like to thank the organizer Science Club for giving me the opportunity to talk about entropy. So as it is written here, do you have a pointer? Yeah. So as it is written here is a sine qua non of scientific enlightenment by George Potter, Nobel laureate, in a BBC video series. So which means that it's absolutely necessary to understand changes that happen around us, and without understanding entropy, we will not be able to interpret them. So as I said, entropy governs the change, and the change that we see every day, for example, we know that sunlight gets absorbed and new matter gets produced, and at the same time, the sun energy gets converted to chemical energy and gets stored. So this is a change of matter and energy. Also we see all around us change of phases, different phases of water, and also different phases of polymorphisms of carbon. Also there are processes happen every day in our life. For example, when we see, it's actually a chemical reactions that goes from a trans to a cis conformation, and that happens only with the visible light. It cannot happen with any other frequency, and therefore we can see that, and that also happens due to entropy. And it also helps us organize, like for example, the organism like human being is made up of atoms and molecules, and that incredible organization that is happening, that also contributes to increase in entropy. So as I said, with rhyming with the Lord of the Rings, there is only one law to rule them all, and that law is entropy. Formal definition of that is, it is reversible heat by temperature, but we will try to understand that in a little bit more different perspective. For example, during 19th century, around 1820s and so, or even started even before that, 18th century and all, people try to understand, make more efficient engines. So we are talking about steam engine here, which is an external combustion engine, and also this is an internal combustion engine, petrol engine, and there is an engine in our body. Yes, our body itself is an engine. So engine is something that takes heat and produces work. Here the ATP gets converted to motions, which is work, and that all that requires an understanding of entropy. So before people knew that, a lot of people tried to make machines that will run forever. That's like free energy. Like you put nothing, but something will run forever. That's called perpetual motion machine. For example, a lot of design came up. One of them is like this. This is a ratchet that can only move in one direction. So therefore, since it cannot move in the other direction, one can extract work out of that and probably will not spend anything, but that will violate one of the laws. And other one is something called perpetual motion machine of the second kind, where you will put, let's say, an ammonia which is in normal temperature under the sun. It will vaporize it, it will produce pressure, and that pressure will run the motor, and it will go, and by running the motor it will get cooled down and again become liquid, and things will go on. In fact, this is the only perpetual motion machine that got an American patent. Of course, the person who did that had to suicide later on, John Gamgee. So entropy tells us that it's not possible to make either the first one or the second one specifically. So what is entropy then? It is considered to be, or it is commonly known to be, an order to disorder transition. For example, when you drop a ball, after some time you will see that it gets stopped and never comes back. If you put it in the floor, it will never come back to your hand. And the ordered motion that was there when the ball was falling converted to some kind of random motions of the atoms of the floor molecule. However, we will see that it is not just order to disorder transition. For example, when you talk about an engine, I will demonstrate one engine here, which is Stirling engine. This came even before people understood the concept of entropy. So this was something like 1818, even before the definition of entropy came about, or much before that. So we'll demonstrate one example of Stirling engine. So I just poured a cup of hot water, and temperature is 72.5 degree. I'm going to put this Stirling engine. So now you see there is a heat here. I put my Stirling engine on top of that and hoping that it will work. So right now the temperature of the top plate and the bottom plate is same. But now when I put the hot water, the bottom plate will get heated up. And if you just wait for some time, okay, now it will keep on going. I'll put it in the floor. So depending on the heat, intensity of the heat, this machine will work, and idea is that one can extract from these motions, any motion in a directional motion, one can extract work. So therefore heat gets converted to work. But is it the heat that gets converted to work? That's the point. Turns out that this Stirling engine will run even on ice. Forget about hot water. So in ice you don't have heat. So what all you need is not the heat, but a difference in temperature between two portions between which you can put an engine. Why you need a difference in temperature and not just heat? The reason is that there is a flow of heat from hot to cold or high temperature to low temperature. So before we talk about that, we'll just okay. So the flow of heat from high temperature to low temperature is what is governed by the increase in entropy. So we will talk about some more examples apart from heat and engines that we see every day around us. For example, if we see this to happen, we will not be surprised, I guess, right? Because this is a very common thing to observe. Then if we see this, so that was, if we see this is very common for us to observe. There is no wonder in that. We will not be surprised because we are habituated to see something is mixing spontaneously. Now, what about this? If we see this to happen, we will be surprised because we know that this is not possible. This is our common observation, that this cannot happen in our normal world. Why it cannot happen? It cannot happen because one of the laws, or the most important one, is prohibiting it to happen, or this one, for example. So if you look at this, you certainly know that it is not happening in our real world, it is happening in a virtual world where we are running the camera in a backward motion. So now if I show you this, can you tell me whether it is running forward or backward? Unless those of you who stood in my class.
Obviously backward, because it actually damps.
You just observe it, it is not damping. So, if you see that till the end of the movie, somebody is holding it to stop it.
Amplitude is increasing.
See, this time I may have run it forward, okay. So the point is that actually if you do it properly, you will not be able to tell, because this is not violating anything by running backward. The other two were violating laws, second law of thermodynamics, or violating the entropy principle, by running it backward, but this one, even running it backward, is not violating it because there is no change in entropy. It is not going negative. So, the two examples where entropy were going negative when you are running backward, but here it is not. Even this one, Raman is, this is a nice one actually. I wanted to show you this one, although it is an older video. You will not be able to say that it is running backward if it is done properly. So, now the thing is that, is it disorder that is happening here? So, this is one example where this is a simulation where there are ellipsoids which have no interactions. So, there is no energy principles here. Now, when you run that, right now the red color means disordered state. They are random.
And as I start this simulation, you'll see by the color green, which we use to denote particles that are ordered locally relative to their neighbors, that
so this is
they
from
start to align, they start
and you
to
can
order
see that they are
with
forming
each other.
green,
And if we
which
run it
means they are
long enough, we
forming
see that this
an
order.
ordered state.
And as I start.
So, it is not that always the disorder that will win or that will go, but of course, there is a correlation with the disorder and entropy, but it is not necessarily true. So, what is entropy then? So, entropy is nothing but options. If you have more options, you have more entropy. So, disordered state may have more options and will correlate with increase. However, it is not always true. So, now then what is entropy then? Entropy is something that every system, if left to itself, will on the average change towards a condition of maximum probability, which means that if it is more probable, it will happen. If it is not, it will not happen. And the famous law that governs that this or dictates that is by Boltzmann in 1872, where he said that entropy is some constant logarithm of microstates or options. If you have more W, if you have more options, you have more entropy. So, we will show some examples of options, how the options can be increased. For example, you have two-level system, you have two states, two options to choose. And if you have n number of particles to choose from, the number of options or number of microstates will be n factorial, this number, NCN1. And if you have more levels, you can write that this way, and you can calculate the W. I'll show you more options. For example, you have 3 particles. Let's say each particle can sit in only one box, and they cannot, like 2 particles cannot. In that case, you have very little options here because you have given one box for one particle. But if you have a little more room, then the number of options will increase, and entropy will therefore increase. If you have more options, it will even more increase, and entropy will increase. So, with options, entropy will increase. Now, let's say with the options, I give you more restrictions. I said, okay, you have options, but under particular condition. And these are the condition that number of particles will be fixed, number of amount of energy will be fixed. And in that case, you will see that when you, by keeping the energy and particle fixed, 3 particles at 3 units of energy, you will see that your options will be varied, and one of them will give you a higher options than the other. And when you calculate their distribution, what you will find is that where the option is limited, the distribution is extremely peaked. This is the options are now a little bit more, distribution is little bit more spread, and here it is much more flatter. So, this one has the maximum entropy. So, what happens is that everywhere the energy is same, but the distribution of energies are different, and each distribution will correspond to a value of entropy. So, that means it is the distribution that dictates, not the value. So, it is the distribution of energy that governs the entropy. That is the most important thing. For us, for the universe, the energy is conserved, we know that. However, at every second, every minute, every microsecond, and even less than that, distribution is changing. When you burn a coal, you are taking the energy that is stored in coal and distributing it to environment. Any process that you can talk about, even when I am speaking, I am distributing energy. Even when I am not doing anything, my body heat is getting dissipated to the environment. So, every time the energy is getting distributed. And even when I am doing some work and trying to store energy in a particular location, I am spending more somewhere else and increasing the entropy. So, increase in entropy is evident, and that is happening every time because the distribution is changing. So this is a little bit more number just to get a better statistics. So now 9 particles and 7 units of energy can be distributed in so many different ways. And then if I calculate the probabilities of having a particular distribution, what we find is that as the energy increases, the probability of occupying that state decreases, which means that higher the energy, lower the probability. And that comes from the same principle of maximization of entropy with these constraints. And that is Boltzmann distribution. And that's why it's followed in different places. So now I'm going to show you some examples. So classically, increase in entropy is an observation, is a postulate. Classically, transfer of heat from high temperature to low temperature is a postulate. It is an observation from which everything is built. However, statistically, it is not a postulate. It can be shown from the other postulate that option increases. And we are going to show that. So let's talk about a 2-level system and 10 particle and total energy 2. So now number of possibilities by which, it should be 4. So number of possibilities by which 4 particle can go to the higher level is 210, and this energy is 2. So number of possible ways that 2 particle can go up is 45. The total possibilities will be multiplication of both, and it will be 9450. So now you see this has more heat because more energy 4, this has less 2. Now I can transfer 1 unit of energy and make them equal. So it will become 3 now. It will become 3, and if it becomes 3, then the number of possibilities will be 120 and 120. When you combine them together, it will become 14400. Remember the last one, 9450. So now when you distribute your energy, your overall possibilities increases, which means that it will be evident for the energy to flow from high temperature to low temperature, and thereby will increase the possibility. So here there is the simulation done by Raman, my student, and you see I'll just start from beginning. So initially there were 200 particles in one chamber, and then this is a bar chart, so the number was more, and you see that so as the time progresses, the movie runs again from the beginning. As the time progresses, the particle numbers become equal in both the boxes. This number is wrong. So energy, there is no energy bias now. So there is no preference for the particle to go from one chamber to the other chamber because there is no advantage in terms of energy. Only advantage that it has is in terms of increasing its possibility. Okay, I got it. What is happening is a Siri. Okay, so now I have calculated that numbers here. One can do that. Now this is a three box system. Energies are all equal 0. Initially everything was here only. Now from 2 level we have gone to 3 level systems, and as you can see that eventually every box will have the same energy, a same number of particles. Why? Because that is what more logical. That is what more possible situations to happen. If you have in a classroom 50 seats, you will come and sit everywhere. It's not that you will come in one particular place every time. So naturally, it will have preference to cover all the 3 boxes. Now, when you go to so here the calculations are there, and one can show that when all particles are in one box, the possibility is really less, and then it will increase with this thing. Now we'll say that okay, now we'll put more constraint. We'll say that the energies are not same in every box. Now you have bias that you got, bias is created. Something will be more energetically stable than the other thing, and eventually what will happen is that the distributions will follow. It will maximize entropy, but with the constraints that it has to satisfy the energy as well. And once you do that, you see you follow a Boltzmann distribution. With the lowest energy, you have highest probability, and the middle, and if you run for longer, you will see the numbers will be 140, 48, and something like that, which will actually follow this Boltzmann distribution based on this average energy. So Boltzmann distribution then is nothing but maximization of entropy under the constraints. In fact, even if you don't have any constraint, for example, let's say you make the energy 0. If you make the energy 0, then you will see that they are equally probable, and that's what was happening when there was no energy. So this is a more general expression for every possibility. So we'll show one more. We show that now we show the effect of temperature. So earlier it was happening at a normal temperature and following Boltzmann distribution, still follows Boltzmann distribution. However, you have increased the temperature. So what will happen? So it will overcome. So now temperature will overcome the bias of energy. It will increase the entropy, and the distribution, it should not be flat exactly, but it will be almost, it will overcome and it will come more or less equal, and that's what is happening. So what we understood is that, fine, time? Okay. So what we understood is that entropy is inevitable, it will keep on increasing for the universe, of course. We may see somewhere local ordering to take place and something else, but remember always the background somewhere the entropy is increasing for the universe, which means that since for the universe entropy is increasing every minute, every second, every nanosecond, where did it start? It must have started long back. So entropy today is more than entropy of yesterday than the entropy of day before yesterday, which means if you go back, the one that we know is the starting point of the universe 13.7 billion years ago. And that now nobody knows about that so well, what happened there. But then we certainly know that it is expanding, the universe is expanding and still is expanding, it's not in equilibrium. You saw that when we could not detect the movement, that is the point of equilibrium where entropy was no longer increasing, and therefore we could not say which direction it was going. But if you see something is moving in certain direction, you know for sure that entropy is increasing, which means it is actually coinciding with the time. So entropy is the arrow of time. We are here today. This plot is very schematic. I don't know how it has increased. We are here today. Entropy was very low at some point, and it will keep on going. And what will happen in that time when it will go? It will keep on increasing, right? It will keep on increasing. Universe will expand. All the energies that were stored will be distributed, and it will stop only when it will be distributed everywhere, equally, every possible places. And if that happens, there will be no organizations. Some energy that are stored in our cells, in our molecules and all that, no longer it will be there. It will be a heat bath in which there will be no molecules, nothing. Even one molecule, one atom will have its stored energy, so nothing will exist. And that is called the heat death. But it will take long time to come. So therefore, we are fine. So thank you for your attention. So yeah, it was still, see, it slowed down actually. It will not run forever. Any questions?
So in the experiment where the temperature differences are there and the entropy is being calculated, if in few boxes space constraint is there, so how then that will going to affect?
Space constraints, right? Like, of course, see, this example that we showed is very, toy example. If you constrain the space, you know that, it will be proportional to the entropy. So that means entropy of the box will be smaller. Entropy of that particular box, if there is a constraint, will be smaller. So if you have a bigger box versus a smaller box, then you should have a difference in the number of particles, because the entropy of the particle in a bigger box should be higher than that of the smaller box. That's a good, actually I didn't try that, I can try that. Right now the boxes are all equal. But if we make them different, that effect also should be seen.
So it's like the energy constraint is there?
There is no energy constraint when the particles were distributed equally. There was no energy constraints. It was just that entropy will be more if they spread over. That's it. Now you are saying that what if the boxes are different, right?
And what if you just put the slit after few seconds on and off, on and off?
Yeah, see, on and off are something, you can talk about a time dependent processes and all. So when you talk about entropy, they are equilibrium processes. That means you wait long enough and then you only measure. See, initially, I forgot to mention one thing. When you saw the number of particles were fluctuating, it's every time the particle is not moving in one direction.
Yes. Yes.
So entropy is true only on an average. Only on the average number, on an average, the particle will move from one box to the other box. But sometimes it can happen that it will go in the opposite direction also. But the probabilities of that is limited, small.
Hello, good morning, sir. As you said, when we are starting from the so-called Big Bang, and the entropy is rising everywhere, entropy should be rising and should be positive for universe. So can we say the overall energy content of the universe is decreasing as entropy is uniformly distributing?
Okay. So the point is that energy is conserved. That's what I try to say. Like if you have 10 units of energy, let's say you have 10 units of energy and it is with one particle only. And then you say that I distribute among 10 particles. And if I add all the energies, it will be still 10. But now every particle have 1 units of energy rather than 10. So energy is conserved, that is not changing. It is just getting distributed, becoming more even. That's it. And that increases the entropy. It is just the distribution that gives a measure of the value of entropy. So if the distribution changes, entropy will change. Okay, so you have the same thing, you are just spreading it over. It will have a different value of entropy.
Thank you.
Okay.